Today, we're going to be reviewing the ideal gas laws. This is just going to be a review for AP Chemistry of what the ideal gas laws are, the equations for the ideal gas laws, and then we're going to go over some practice problems. So, quick topic overview of what we're going to discuss. We're going to discuss what STP is, what Boyle's law is, what Charles' law is, Gay-Lussac's law, the combined gas law, Avogadro's law, and then the ideal gas equation. And then we'll go into some example problems after going over each of these topics briefly. So, what are ideal gases? They're gases whose behavior is highly predictable and it happens at low pressures and high temperatures, also known as STP, the standard temperature and pressure. So this is the definition of an ideal gas, is when the temperature is 273 Kelvin. Note, it's very important to use Kelvin for all these equations instead of Celsius. So you always want to remember the conversion from Celsius to Kelvin is just adding 273.15 to your degree of Celsius. And that's just the equation no matter what your temperature in Celsius is. And then the ideal pressure is 1 atmosphere, 1 atm. There are 5 main different ways to write pressure. So there's ATM, KPa, BAR, torr, and mmHg. The most common is going to be ATM followed up by torr. You don't really see the other ones a lot, but I just wanted to include it because it's always good to know in case you encounter them in a problem, which you never know when you will. So let's start with what each law is. So first, let's start with Boyle's law. So this is for when gases are held at constant temperatures. Pressure increases when volume decreases, and vice versa. So pressure 1 times volume 1 equals pressure 2 times volume 2. So that is the Boyle's law equation. Moving on to Charles' law, this is for gases that are held at constant pressures. So this says when the volume decreases, the temperature also decreases at a constant pressure. So the equation for this, volume 1 over temperature 2, is equal to volume 2 over temperature 2. Okay, let's go on to Gay-Lussac's law. So this is when something's held, or when a gas is held at a constant volume. So this means pressure and temperature are directly proportional. So when pressure decreases, so does temperature, and vice versa. So pressure 1 over temperature 1 equals pressure 2 over temperature 2 is the equation for Gay-Lussac's law. So now we're moving into the combined gas laws because we have those 3 basics for when it's a set pressure, a set temperature, or a set volume. So now if we're working with multiple gases, so pressure 1 times volume 1 over temperature 1 equals pressure 2 times volume 2 over temperature 2. That is the equation for the combined gas law. Now, moving on to Avogadro's law, this is now going into the number of moles and the number of molecules in the gases. So we're focusing away from just pressure, volume, and temperature, and now going into like the amounts. So at STP, which is the 273 Kelvin and 1 atm, if gases have the same volume, temperature, and pressure, they have the same number of molecules. So that means if you have 1 liter of argon at 273 Kelvin and 1 atm, and you also have 1 liter of neon at 273 Kelvin, 1 liter, and 1 atm, those are going to be the same number of molecules. So the equation for this is volume 1 over moles 1 equals volume 2 over moles 2. The other great thing to note about this is any 1 mole of gas at STP is equal to 22.4 liters. So if you have 1 mole of whatever gas at STP, you immediately then know the volume. This is a really quick and easy trick and is also necessary to solve a lot of problems. It also saves a lot of time. Just a no-brainer to have that in your memory. So now let's go over the ideal gases equation. So this is the general equation you can either find pressure, volume, moles, or temperature from this equation. And the equation is pressure times volume equals moles times R constant times temperature. So pressure, obviously P stands for pressure, V stands for volume. Lowercase n is what stands for moles in the gas laws. And then R is a constant specifically for this ideal gas equation. And it is 0.08206 liters times ATM over Kelvin times mole. That is the constant for R. And the reason they have all the different, they have the pressure and the temperature and the amount of moles in the R constant is so you can cancel it out for your equations. So you're left with the correct unit at the end. And then obviously T is for temperature. Just another reminder, temperature must be in Kelvin for all of these equations. And again, to convert from Celsius to Kelvin, you just take whatever number you have in Celsius, add 273.15. But you have to do that for every single ideal gas problem you have, or you will get a completely wrong answer. Now we're going to move on to some practice problems, some practices for the ideal gas laws. And what I'm going to do is I'm going to say each problem, give you about 30 seconds to work on it. You can pause the video if you need longer. And then I'm going to go through step by step on how to solve it. So this first problem says a sample of 0.01 moles of nitrogen dioxide is combined at 127 degrees Celsius and 2.5 atmospheres. What would be the pressure of this sample at 27 degrees Celsius and the same volume? So I'm going to give you a few seconds and pause if you need longer. All right, so we're going to go over this real quick. And so what I'm going to do is I'm going to pull up some notes here and we're going to work through it on my screen. Okay, so, hop to practice problem 2, my bad. Okay, so what we know is we have 0.01 moles of a gas. There we go, 0.01 moles. And it's 127 degrees Celsius, which we already know we're going to need to convert to Kelvin because, as I said, all temperatures need to be in Kelvin. So for that, I just do 127 plus 273.15, and that's going to give me 400.15 degrees Kelvin. And then we have 2.5 atmospheres. So then we know that the volume of this will stay the same. So the volume of this will be equal. We know that the new temperature is going to be 27 degrees Celsius. So we're going to go 27 plus 273.15, which gives us with 300.15 Kelvin. And we're looking for the new pressure. So that is what we're trying to find. Question mark or X equals ATM. So looking at this problem, I'm seeing that we're going to have a constant volume, which means we can use Gay-Lussac's law because that states at a constant volume, the pressure and temperature are directly proportional. So Gay-Lussac's law is, again, P1 over T1 equals P2 over T2. So now let's fill in the information we know. We know P1 is 2.5 ATM. And we know T1 is 400.15 Kelvin. And that's equal to P2, which is the question mark, so X over. And then T2 we already know is 3. Oops, I accidentally drew 2, sorry, my bad. We know is 300.15 Kelvin. So now we just need to find X, and for this I'm going to hop onto my calculator and go into the equation section of my calculator. because that makes it extremely easy, and you just enter the problem as you have it written down. You've already done the hard work. Now it's just solving. So we know that 2.5 over 400.15 is equal to x over 300.15. You just put that into your calculator, click the solve button, and I'm going to get that x equals 1.875. And the numbers go on. I'm just rounding to 4 significant figures because that's what we have up here. Oh, my bad. We have 2 significant figures. So I'm going to just round that, to 1.9 ATM. Because we're matching significant figures up here. Again, the significant figures is not the most important thing, but in ideal gas laws, but it's always important in chemistry, so it's always good to keep good habits. Okay, so a way to double check this, if you aren't sure, is you can go 2.5 divided by 400, 400.15 Kelvin. You can see the answer to that, and then you can go 1.9 divided by 300.15 Kelvin. They should be about the same. The numbers might be a little bit off because we did round to get to that, but I'm seeing that the numbers are both exactly the same for those equations, and so that means they're directly proportional and equal. So that would be our answer to practice problem number 1. All right, so now let's move on to practice problem number 2. What temperature will 0.654 moles of neon gas occupy at 12.3 liters and at 1.95 ATM? So I'm going to give you a second to work on that before I hop in and solve it. Okay, so I give you a little bit of time to think. Pause the video if you need more time, but we are now going to solve this. So again, I always like writing what I know. So I know there's 0.654 moles of this gas, of neon. I know there's 12.3 liters of neon, and I know it occupies 1.95 ATM. I also know I'm trying to find temperature, so I'm trying to find X here. So, looking at this, I immediately see I'm going to have to use PV equals nRT to solve this equation, because we have pressure and volume, and we have moles, and we're just trying to find temperature. So again, that equation is written like this. But now we run into a problem because we want T to be on the left side of the equation. So we gotta use some simple math and rewrite this as T equals PV over nR. So it's simple switching around to get that equation. So now we're going to fill in the information. So we have T equals, P is going to be 1.95 ATM times V, volume is going to be 12.3. Always remember, put your units here to not get confused. And then over N is going to be 0.654 moles. And then R is going to be that constant, which is again 0.08206 liters times ATM over Kelvin times moles. Okay, so now we're going to start canceling out units. So we see ATM, ATM. I see liters, and I see liters. I see moles, and I see moles. So I have those canceled out, and now I just have K left, which is temperature, which is what we're trying to find. So now it's just as simple as putting this into a calculator. So that's going to be 1.95 times 12.3 divided by 0.654 times our constant 0.08206. And then put that into your calculator. You should get 446.9 or somewhere around that. So I'm going to write that. I'm going to round that up to 447. This keeps exiting, my bad. So we know that the T is equal to 447 Kelvin. And it doesn't say what unit this has to be in, so 447 Kelvin should be perfectly adequate for your unit, because it doesn't specify it needs to be in Celsius. So there you have it, the answer to practice problem number 2. Now we're going to jump on to practice problem number 3. And this problem says, a volume of 26.5 milliliters of nitrogen gas was collected in a tube at a temperature of 17 degrees Celsius and a pressure of 737 mmHg, so a different pressure than ATM. The next day, the volume of the nitrogen was 27.1 milliliters, with the barometer still reading 733 mmHg. So what was the temperature on the second day? So I'll give you a minute to think. Okay, so now that I've given you all a second to think, let's write down what we know. So we know this is going to be before and after. So the before we know is 26.5 milliliters. And we know 17 degrees Celsius. We know we have to convert that. So 17 plus 273.15 to get that Celsius into Kelvin. And we know it's going to be 290.15 Kelvin. And then we know the pressure, 737 mmHg. So now we're looking at the after. So we're going to see, we see the volume was 27.1 milliliters in the after. And we are looking for the temperature, so that's going to be our variable. And we know the pressure stayed the same. So from this, what law are we going to use? Well, we see the pressure is a constant, so that means that we can use Charles' law, which shows V1 over T1 equals V2 over T2. So we can start filling in the information we know here. So V1, 26.5 milliliters over T1, 290.15 Kelvin equals V2, so we know that's 27.1 milliliters over X, because we're trying to find T2, which will be our variable X. So now this is again as simple as going into your equation setting on your calculator and entering it into the solver function. So I'm just going to type it in here. So we're going to see 26.5 over 290.15 equals 27.1 over X. Let's put that in. And you should get 296.719434. And so you can just round that to 296.72. And that again is going to be in Kelvin. And that is how you solve this equation. Thank you so much for coming into this chemistry review. I hope it was useful and I hope you enjoyed it. And I hope this just caught you up a little bit, reminded you about the gas laws and how to solve them and look at them.